Here is the full script. A comet is already gone by the time you decide to chase it. That's not a metaphor, that's orbital mechanics. The moment a comet swings into the inner solar system, blazing past the sun, shedding gas and ice and dust in a tail that stretches millions of kilometers, it is already accelerating away from you. By the time mission planners run the numbers, engineers build the rocket, astronauts train, and the launch window opens, that comet is somewhere else entirely, somewhere much harder to reach, and the trajectory to catch it curves through a region of space so far from Earth that the word distance stops feeling like a real thing and starts feeling like an insult to the scale involved. This is what chasing a comet actually means, not the romantic image of a spacecraft pulling alongside a glowing icy mountain while astronauts float out to take samples. The reality is a pursuit problem with a moving target, a fixed fuel budget, a human body that was never designed for deep space, and a return trip that the physics of this universe may simply not permit. Comets fall into a few categories, but the ones worth chasing, the ones that capture human imagination, are the long-period comets. Objects that originate in the Oort cloud, a vast spherical shell of icy debris surrounding our solar system at distances up to 100,000 astronomical units from the Sun. These comets spend millions of years in frozen darkness before something nudges them inward. A passing star, a gravitational wobble, and suddenly they're falling toward the Sun on trajectories that take centuries or millennia to complete. Halley's Comet returns roughly every 75 years. That's considered a short-period comet. The long ones, some won't return for 10,000 years, some won't return at all. They pass once, and they're gone forever. We've dreamed about visiting them for decades, and the dream has a solid foundation. Rosetta didn't just fly past Comet 67P, it orbited it. The Philae lander actually touched down on a comet's surface in 2014, bounced twice due to the near-zero gravity, and wedged itself into a crevice in the shadow of a cliff. That was a genuine human achievement. Stardust collected dust samples from Comet Wild 2 and returned them to Earth. Deep Impact fired a copper impactor into Comet Tempel 1 to study what lay beneath the surface. We have done extraordinary things in comet science. The dream of sending humans to one is not born from ignorance. It's born from genuine curiosity and the natural extension of what probes have already done. But here's where the dream collides with a wall that no amount of ambition can move. To reach a comet, you don't just need to aim at where it's going to be, you need to match its velocity. This is the part that most people don't fully appreciate. If your spacecraft arrives at a comet's location while traveling at a different speed or in a slightly different direction, you don't land on it. You fly past it in seconds. The relative velocity between your spacecraft and the comet could be tens of kilometers per second. At 30 kilometers per second, two objects pass each other in the blink of an eye. There's no hovering, there's no slowing down to have a look around. You have to arrive at exactly the right position, traveling at exactly the right speed, in exactly the right direction, and then, if you want to come home, you have to do all of that in reverse. Comets in the inner solar system move fast. Halley's Comet, when it swings closest to the Sun, is traveling at roughly 54 kilometers per second. The Parker Solar Probe, the fastest human-made object ever launched, reached about 163 kilometers per second at its closest solar approach, but that speed comes entirely from falling toward the Sun. Using it to match a comet's velocity on its outward leg, carrying a crew, carrying life support, carrying return fuel, is an entirely different problem. The fastest we've ever accelerated a crewed spacecraft, the Apollo missions at translunar injection, reached about 10.8 kilometers per second. The gap between that and what a comet rendezvous demands is not an engineering challenge, it is a civilizational challenge, and we are nowhere near solving it. The rocket equation governs all of this, and it is merciless. To accelerate mass, you burn fuel. But that fuel is itself mass, which also needs to be accelerated, which requires more fuel. The relationship between the mass you want to move and the fuel you need to move it is exponential, not linear. For a crewed mission, carrying enough life support for a journey that could last years, enough fuel to match a comet's velocity, and enough reserve propellant to make the return trip. The fuel-to-payload ratio becomes absurd. You would need a spacecraft of staggering size just to move a relatively small crew capsule. Chemical rockets, the technology we actually have, don't come close to producing the efficiency needed. Ion drives produce accept. Ional efficiency, but thrust measured in millinewtons, roughly the force of a single sheet of paper resting on your hand. Adequate for an unmanned probe with years to accelerate, useless for a crewed mission on any realistic timeline. Nuclear thermal propulsion could theoretically double the efficiency of chemical rockets. Nuclear pulse propulsion, essentially detonating nuclear bombs behind a spacecraft, could do better still. But none of these systems exist in crude mission-ready form, and even the most optimistic projections for nuclear propulsion don't bridge the full gap between what we can do and what a Comet rendezvous demands. Antimatter drives and fusion rockets exist in theoretical papers. Theoretical papers don't carry people to the outer solar system and back, and then your body registers its objections. Deep space beyond the protection of Earth's magnetic field exposes the human body to galactic cosmic rays, high-energy particles traveling at near-light speed, originating from supernovae across the galaxy. Unlike radiation from the sun, which can be somewhat shielded, galactic cosmic rays punch through most materials we can practically carry on a spacecraft. They punch through you. They strip electrons from atoms in your DNA. They cause double-strand breaks in the double helix. The kind of damage that, accumulated over months and years, dramatically elevates the risk of cancer, cataracts, and central nervous system degradation. Studies on astronauts who spent extended time aboard the International Space Station show measurable cognitive changes, slower processing, reduced memory function, from radiation exposure that was still partially protected by Earth's magnetic field. A mission to a comet would expose a crew to radiation doses many times higher. Simultaneously, weightlessness is quietly dismantling the body from the inside. Without gravity's constant resistance, bones shed calcium at a rate of roughly 1 to 2% per month in the most affected regions. The spine, the hips, the femur, the bones that carry load on Earth and have nothing to carry in space. Astronauts returning from 6-month ISS missions require months of rehabilitation just to walk normally. The fluid that normally pulls in your legs redistributes upward, pressing against your optic nerves. Roughly 70% of astronauts on long-duration missions experience measurable vision changes. Some are permanent. Your heart, accustomed to pumping blood upward against gravity, begins to shrink and weaken because the demand has decreased. Your immune system, deprived of the microbial challenges that keep it calibrated, begins to dysfunction. Latent viruses in your body, herpes strains, dormant since childhood, begin to reactivate. A mission lasting 2, 3, 4 years does not give these systems time to recover, it gives them time to cascade. And then the comet itself presents its own particular lethality. Comets are not quiet objects. They outgas violently. Jets of carbon dioxide, carbon monoxide, and water vapor erupting from the surface as solar heating drives sublimation. Rosetta watched Comet 67P at CL, O's range and documented jets that would catastrophically affect any spacecraft attempting to maneuver nearby. The nucleus is structurally inconsistent, loose rubble and ice layered in ways that make anchoring nearly impossible, as Feely demonstrated. The coma, the cloud of gas and dust surrounding the nucleus, would sandblast any spacecraft. Dust particles moving at comet velocities carry kinetic energy proportional to the square of their speed. At those velocities, particles far too small to see with the naked eye impact with the force of small projectiles. Every hour in the coma is a lottery. A micrometeorite strike against a critical system, life support, navigation, propulsion, ends the mission and everyone on it, with no rescue possible, no recovery, no emergency return. The nearest help is measured not in hours, but in the communication delay alone, potentially 40 minutes each way for a signal traveling at the speed of light. By the time a distress call arrives on Earth, whatever went wrong has already been resolved by physics, one way or another. This is why anyone chasing a comet will never return, not with current technology in any near-future projection, not because engineers lack creativity or scientists lack ambition. Because the problem is not primarily an engineering problem. It is a physics problem and a biology problem layered on top of each other. The velocity required exceeds any crude propulsion system that exists or is close to existing. The fuel requirements violate practical mass constraints by orders of magnitude. The radiation environment attacks the human nervous system and DNA over timescales that a comet mission would inevitably span. The weightlessness systematically degrades the cardiovascular, skeletal, and immune systems faster than any intervention we currently have can fully counter. And the comet itself is an active, unpredictable, outgassing object surrounded by a debris field that treats spacecraft with indifference. To reach it, you burn everything. To survive near it, you need shielding we cannot carry. To return from it, you need fuel you could not have brought. The word for a journey with no return is not an expedition, it is something else. But we have touched a comet. Not with hands, with mathematics. with the cold elegance of orbital mechanics that allowed a European spacecraft to travel 10 years and 6 billion kilometers to enter orbit around a mountain of ice and rocks smaller than a city. With the audacity to drop a lander onto a surface that had never felt contact with anything made by conscious minds. We pointed instruments at frozen material that predates the Earth itself and asked it questions. The answers came back in data streams traveling at the speed of light, received by dish antennas on a planet where the people who built Rosetta had grown old waiting for it to arrive. We are creatures of one world, almost certainly forever. Our bodies were sculpted by 4 billion years of one particular gravity, one particular radiation environment, one particular atmospheric pressure. The cosmos did not design us to leave, but it did give us an extraordinary ability to understand where we cannot go. And that understanding, that capacity to measure our own limits against the scale of the universe, is not a failure. It is the most remarkable thing in the known galaxy.